Lesson 9, fission and fusion reactions. All right, so what we're going to be talking about is fission and fusion, either splitting up of larger nuclei or coming together of smaller nuclei to make a larger one. So one of two ways, so either splitting, taking a big one, making two, or making two smaller to make a large. Once again, it's all about trying to become more stable. Stability is the game. All right, so in 1919, Rutherford bombarded stable nitrogen-14 with alpha particles to transmutate. So this is artificial transmutation, forcing something to mutate after. So in this case here, we have nitrogen, we're adding the alpha. So in this case here, we're following the same conservation rules as we did before. We want to make sure there's 18 on top, 14 plus 4. We still have 18 down below, and the charge is down below, which is 7 and 2, 9, 8 and 1 is also 9. So in this case here, we now have two objects, and we can transmutate it, changing form from nitrogen to oxygen, just by hitting it with a alpha particle. Once again, nitrogen was stable, but technically it turned it into an unstable particle, which then was able to produce oxygen. All right, after this, scientists tried to create new elements by accelerating them and launching them into other elements. So it says ES, Einsteinium, maybe? I'll have to double check. 253 is bombarded by a particle. As a result, MD256 is artificially created and a neutron is emitted. Identify the unknown particle. So hit by a particle to produce. So let's see what happens here. So let's write out our ES 253. And looking at my periodic table real quick here. ES. Einsteinium, yep. And that's naturally 99. So I'll put 99 here. Plus something produces MD, Mendelevium, and that is 256. And naturally, it is 101 is the number of protons, and that's MD. But then it says also produces a neutron, and remember, a neutron is a 1, 0 neutron. So all we're doing here is using conservation of nucleons, conservation of charge to determine the missing element that was, or particle that was there. So if you take a look here, we have 253, and here we have 256 plus 1, so that's 257. So it must have been a 4 on top. 99 plus what equals 101? Well, the answer is 2, and therefore we know it must have been an alpha particle. So in questions like this, it's all about conservation. Just make sure you take the top numbers, make sure they're conserved. That's conservation of nucleons. And then the bottom numbers, which is conservation of charge. All right, so the first one we're going to do is fission reactions. This is when a large nucleus splits into two smaller. So in this case here, a neutron hits a uranium 235. Technically, temporarily, it turns into a uranium 236 and then breaks into this two, what we call daughter nuclei. So once again, uranium plus a neutron gives us barium and krypton in this case. And as a result, we were producing 3 neutrons. So the way we're going to show that it's going to be multiples, we're just going to use brackets here to show that there is now 3 of these neutrons. And then it also looks like there's going to be some extra gamma radiation. Sometimes we just say energy. In this case, that energy could be the form of a gamma. The 3 neutrons can then trigger new reactions. This is a chain reaction. So what I want you to imagine is that here we have one object here, and then it breaks. And as a result, yes, it has 2 smaller products, which is the barium and the krypton, but also launches these 3 very fast neutrons that are flying across. So here's a neutron, here's a neutron, here's a neutron. But remember, in order to get uranium to turn into this, it was hit itself by a neutron. So technically, if you imagine that we have another uranium here and another uranium here and maybe another uranium here, and each of those are then hit by another one, and in that process also releasing 3, also releasing 3, also releasing 3. So just in terms of quick numbers here, let's say there's a few mega electron volts released in this. In terms of energy, let's say there's, 200, just a ballpark number, mega electron volts, which that's not too bad. But now each one of these are also 200, which means in this process here, there's actually 600 mega electron volts. And you can see how quickly this can escalate and how maybe out of control this could be if we don't have a way to basically slow down these neutrons or control it. All right, so it says if controlled, it's a reactor. If it's uncontrolled, we consider this to be a bomb. So this can be, a bomb, a nuclear bomb, right? So in this case here, advantages, easy to trigger, only needs low energy neutrons, at high yield, higher than coal, almost 2 million times more. So per mass, you're going to get a lot more energy from that of uranium. Disadvantages, of course, there's radioactive waste, which is expensive to dispose of, costly to the environment, and it is technically a non-renewable resource. All right, so let's take a look at this. Uranium-235 is bombarded by a slow-moving neutron. It then splits into two smaller nuclei. One of them is ZR96, and 3 neutrons are emitted. What is the other daughter nucleus? So same process here. We're just going to write it all out. So uranium-235. Uranium, we should know this one. We should get familiar with it. It's going to be 92 every time. Plus a slow-moving neutron, so we have to include that neutron. And then produces 2 smaller, one of them being ZR96. So if you take a look at ZR, I'm trying to use my sheet here. Zirconium, and that's number 40. So it's going to be 96 on top, which is number of nucleons, and 40, which is number of protons, which must remain constant. Plus something, blank, will then give us 3 neutrons. And remember, we're just going to put 1, 0, and then put the 3 in front of the brackets there. So taking a look at our numbers here, if we take my 235, we need to make sure that we're adding the additional 1. So we have 236. And then at the end, we're going to subtract 96 and then also subtract 3. And I'm left with 137 on top. And then same with the bottom. We have 92 at the beginning. We are then taking away 40. And since neutron has no charge, we don't have to take any off there. We end up getting element number 52. And then once again, this is where we need our periodic table to tell us it's tellurium. So that's Te. All right, so that is how fission works. We have a chain reaction. Neutron hits uranium. Most cases it's uranium, but in other words, it's a large unstable nucleus, and it splits into 2 smaller ones, which would then increase stability. It's not always barium and krypton, as you can see here. Other cases could also be possible. Once again, you just need to follow the conservation rules to solve these ones through.